So our first concept that we're talking about today is a property of equality for exponential equations. And off to the side, there's a definition, very small, but I think it's legible. It says an exponential equation is an equation that contains variables in the exponents. So if you have an equation with variables in your exponents, or variables as exponents, or within the exponent themselves, that would be an exponential equation. So that's what we're going to be starting off by solving today. This one says that two powers of the same base are equal if and only if their exponents are equal. And then there's some stipulations around what's going on here. But it says if you have a base value that's greater than 0 and not equal to 1, then if you have two base values taken to exponents that are equivalent, that means that the exponents are equivalent. So for example, off to the side here, let's just use some regular numbers to talk about what that means. Somebody give me a base value for a number that isn't extremely big. Somebody give me a base value. Just any number that's relatively small. 7, great. So we're going to say 7, leave some space for an exponent equals 7. So base values are the same, BB, both 7. Now this says that the exponents, if you raise them to an exponent, the actual powers are only equal if the exponents are also equal. So somebody give me a number for an exponent. 3? Okay. What's another way of writing the number 3? How else can you write the number 3 aside from just writing one number for 3? What's another way to get to 3? What's that? 3 times 1, sure. 2 plus 1, right? The cube root of 27, right? Those are all different forms of 3, aren't they? So actually, let's do that. Cube root of 27. Are those two things equal to each other? So basically what we're saying is that 3 is equal to the cube root of 27. Is that true? We're just using this over here. If we have two bases that are the same, and we have two exponents written differently, but they have the same value, that means that we can get rid of the bases and say that the exponents are equal to each other. And since 3 is equal to the cube root of 27, then those two powers are equal to each other. I think it's like 343 or something like that, 7 cubed. Yeah, 343. So those each equal 343. So that means that as long as the bases are the same and you have an equation, the exponents would also be equal to each other. Does that make sense? That the exponents would have to be the same if these base values are the same and we have an equation? That's basically what we're saying here. So if we have this, solve an exponential equation using a common base. So what this is saying is we are going to convert these two separate bases, 1/2 and 4, into a common base. So can you think of a base value that we can relate both 1/2 and 4 to? It tells you in the next line. What does it say? What's our new base going to be? Write them using powers of what? 2. How can you rewrite 1/2 but written as a power of 2? The question here is 2 is equal to 1/2 to what power? Or yeah, 2 is equal to 1/2, or not 1/2 to what power? 1/2 is equal to 2 to what power? Sorry. So basically we're asking ourselves for this first part here, 1/2 equals 2 to what power was it? -1, yeah. So we could rewrite what's inside the parentheses here as 2 to the -1 power to the x plus 7. Because 2 to the -1 is 1/2. The other question here is 4 is equal to 2 to what power? 2, yeah. 4 is equal to 2 squared. So we could write the other side as 2 squared to the 3x. So we've leveled the playing field here. Now the base values are equal. Does everybody see what we just did? Converting those to make sure we have the same base value. All right. So when we're dealing with exponent rules, you're allowed to multiply exponents with a power to a power. So we can actually get rid of this exponent and combine it with this exponent. Because power to a power means multiply this exponent by that exponent. So this would be 2 to the opposite x minus 7 equals 2 to the 6x. Are there any questions about what we've done right now? Power to a power, this is an algebra 1 concept right now. Power to a power means you multiply the exponents. -1 times x plus 7 is negative x minus 7. 2 times 3x is 6x. Now that our bases are the same, what are we allowed to do now with our exponents? What do we do with our exponents over here? We got rid of our bases, and what did we write instead? We just wrote the exponents equal to each other, right? So now that our bases are the same, we can write our exponents equal to each other. So we're going to have negative x minus 7 equals 6x. And then we just solve for x. You can add x to both sides. That's negative 7 equals 7x. And then x equals -1. Yeah. All right. Any questions on what we just did? We're going to do a couple more examples doing this exact same process before we move on to our next example, but our next type of example. But what we're doing is we're equalizing the bases. And once we've got our bases equalized, we can then set the exponents equal to each other and then solve for the variable. So that's the whole idea about what we're doing. So are there any questions about details about what just happened? All right, let's keep going then. For A, right now we have bases of 25 and 125. What will our common base be? What number could we rewrite with the same base between those two? What is it? 5, yeah. 25 is equal to 5 to what power? 2. So we can write 5 squared to the 3x power is equal to 5 to what power equals 125? 5 to the 3rd power. So it's 5 cubed to the x plus 2 power. Now we have to use the power rule. So we have to multiply our 2 times 3x, which we did in the last problem. That was 6x. So this is 5 to the 6x power equals 5 to the what power? Yeah, 3x plus 6. Good. Basically, kind of like using the distributive property, but with the exponents. All right, so now that we've equalized our bases, let's set both exponents equal to each other. So it'll be 6x equals 3x plus 6. Subtract 3x, that means 3x equals 6. So what does x equal? 2, yeah, x equals 2. Nice. Try B on your own. Figure out what base you need to use. I'll give you a hint. One of the two numbers already is using the base that you need to use. What's our common base going to be? 10. Okay. What does this look like as 10 with what exponent is this going to be with 10? -3. Good. That's 10 to the -3. That's 1/1000. If you write it as a fraction, it's 1/1000. To get to 1,000, you raise 10 to the third power, but to get to 1/1000, you raise it to the -3 power. So 10 to the -3 equals 10 to the 6x. There's no power rule that we need to use here. We can just straight up set those two exponents equal to each other now. And so that'll be -3 equals 6x. What does x equal? -1/2. Good. There we go. So I think, honestly, the hardest part of this process here is going to be figuring out which base is the same between the two values. And that's only if you can write a common base between the two. What if you can't write a common base between the two? That's what we're going to take a look at next.
How do you figure out the 10 to the -3?
0.001 is 1/1000, right? So 1/1000, if you want to write that as a fraction, is that, which might make it easier to figure out that this needs to be -3. Because 1,000, if this was the reciprocal, 1,000 would be 10 cubed. So to get 1/1000, the fraction version of it, it would be 10 to the -3. Other questions here before we move on? Okay. If your bases are not the same, or if you can't create common bases, how could we rewrite this potentially using logarithms instead of figuring out a common base? Honestly, it's going to be kind of the opposite of what we just did. So for example, there is no common base for 17 and 4. There's nothing that we can, there's no way we can rewrite these using a common base. That's not a possibility. So think about moving in the opposite direction. Imagine for a second that those two things are the exponents. Because what we just did is we said, all right, if we have the exponents that are the same, that means whatever the base was, those were raised to those powers. The same base was raised to each of those powers. Same thing over here. The same base was raised to each of these powers, -3 and 6x, and that base was 10. Over here, the exponents were 6x and 3x plus 6, and 5 was raised to both of those powers. So as long as you use the same base, technically you can create whatever base you want to use. It doesn't matter. But right here, it says to write each of them using a power of 10. And that's because when you use a power of 10, you don't have to do a special log base. You can just use log as opposed to log base something else. So what this is suggesting is treat these like the exponents, which means we can rewrite 17 equals 4x as 10 to the 17th power equals 10 to the 4 to the x power. Treat those two things as the exponents and then put a base of 10 with them. Because if it works from here, rewriting it like that, it has to work from here, rewriting it like that. It's just basically working the opposite direction through that process. Everybody see that? Like there's really not, there's no difference between going from here to here and going from here to here. If we're allowed to work one way through a process, we're allowed to work the other way through the process, especially with an equation. So then right here is your big clue. We're going to use logarithms. So how can we rewrite this using logarithm? Well, because these are both base 10s, we can just rewrite it as this right here. Because as long as we're using the same base value, we can use that log base for each side. And we're still trying to figure out what x equals. So now we need to use one of the rules that we learned over the last couple of days. And that particular one is going to be the power rule. Because if you have an exponent with your logarithm, how can you rewrite that? Talking about the right side of this equation right now. How can we use the power rule of logarithms to rewrite this right side? The left side isn't going to change right now, so we're going to keep log 17. But how can we rewrite this using the power rule of logarithms? The power rule of logarithms, or the power property of logarithms, says that if you have a log of a base with an argument that has an exponent, that's equal to the exponent of the log base with that argument. So basically, you can take your exponent with the argument and put it in front of the logarithm to get it out of being an exponent in that form. So how can we rewrite this? X log 4, good. And the reason why that's helpful is because now we only have to do one thing to get x by itself. What do we have to do to get x by itself? What's that? Close? Yeah. Divide by log 4 on both sides. So this is going to be log 17 divided by log 4 equals x. It's kind of like using the change of base formula that we used yesterday. It's not the same thing, but it's kind of like it. So we're going to have to use our calculator here to get this finished up. So what's the answer going to be? Was that 2.44? Okay. So x is approximately 0.04. Wait, what?
2.0.
Okay, 2.044. That makes more sense. And the reason why I say that is because if you look at this, what's 4 squared? 16, right? So just a little bit more than 2 should get us to 17 with an exponent, and there it is, 2.044. 2.44 would have given us a number a lot bigger than 16, but still less than 64. But it'd be closer, yeah, it would definitely be bigger. So yeah, that looks good. And that definitely makes sense as an answer for this initial question. All right, let's keep going unless there's questions here. Okay, so how could we rewrite this using logarithms? And by the way, you do not have to write the middle step showing the base 10. Because as long as you do the same thing to both sides, it's allowed. The only reason why I showed you this is because we wanted to use a base 10 and then convert to a logarithm. But now that we know that, we could just rewrite this as log 5 to the x power equals log 12. You don't have to write 10 to the 5 to the x equals 10 to the 12th power. Before we even start in on answering this question, though, somebody give me an estimation of what x should equal. 5 to what power is going to equal 12, roughly? What do you think? Is it going to be more than 1? What's 5 to the first power equal? 5 to the first power is what? 5. Okay. What's 5 squared? 25. So x should be in between what two numbers? 1 and 2. Okay. So let's keep that in mind because we're going to be using our calculators a lot for these. And here's something that happens, and it happened to me when I was in high school as well. Sometimes I didn't think about the reasonableness of the answer that I got on my calculator. I just trusted that that answer was correct, but I was prone to typing things into my calculator incorrectly. And if you trust your calculator, which you should, but you should only trust it if you know how to use it correctly. And if you mistype something, hopefully you have an idea about whether or not that answer is reasonable. If you end up with an answer of like 7, that's not going to make any sense for this because 5 to the 7th power is not 12. It's going to be between 1 and 2. So our answer needs to be between 1 and 2. If it's not, then something didn't go the way it needed to. So x log 5 equals log 12. Divide both sides by log of 5. So x is equal to log 12 divided by log 5. If somebody divide log 12 by log 5, what do you get? 1 point what? 1.544? All right. So x is approximately 1.544, which is between 1 and 2. That makes sense. We're just going to keep going with this. So the next one, because honestly, we weren't actually supposed to solve these. We were just supposed to rewrite these in logarithmic form like here. But now that we've solved a couple, let's keep going. The next one actually talks about the equation. So it says as long as x is greater than 0, which your exponent, not your exponent, sorry, your argument needs to be greater than 0 because you can't use an exponent to get a negative number. So your argument has to be greater than 0. It says that if you have 2 logarithms that are equal to each other, that means that the arguments are equal to each other. So that means if the arguments are equal to each other, then you can put logarithms with a common base and make them equal to each other, which is exactly what we just did up here. We just are writing it with a log base 10, because that way we can just use the log button without having to use the log base button on our calculator. We could have, I mean, you could choose any base value you want. It doesn't matter. Log base 10 is just the easiest one to use because it's the simplest way to get to it on your calculator. So here we go. Rewrite this in logarithmic form. What is it going to look like? And let's use log base 10. So what should we write for our equation to get this going? Somebody tell me what it's going to look like. So log 3 to the x plus 1 equals log 5 to the x. Good. And we're going to use a property in a way that we haven't really used it before. But I'll show you what this looks like here. So we're going to have x plus 1 log 3. We've done that before. We're just using the power rule here, the power property. And this is going to equal x log 5 over here. So we bring down our exponents using the power property for logarithms. And then this right here is going to be the product property of logarithms. We're going to be able to add the 2 logarithms together because they both have exponents. Or I guess there is an exponent of both x and 1, which means we can separate these out into x log 3 plus 1 log 3, or just log 3. And that equals x log 5. So that's using the product property for logarithms. I'm going to do something next, and I want you to tell me what just happened, all right? I'm going to write this. X log 3 minus x log 5 equals negative log 3. What just happened there? I subtracted log 3 to get it to the right side, and I subtracted x log 5 to get it to the left side. This is no different than solving an equation that has variables on both sides. In fact, this is an equation that has variables on both sides. And if you're trying to solve an equation that has variables on both sides, you need to get both variables to the same side. And since both sides had x, we need both x's on the same side. We just brought it over by subtracting x log 5. And we moved the one that didn't have the variable to the other side by subtracting it to the other side. Everybody see what happened there? So this is a straight up algebra move here. It just has the word log. Other than that, there's really no difference. Now, both of these have an x. What does that mean for us here? Well, we have a factor, right? X is a factor of both of these. It's actually an exponent of both of these. But kind of like how we applied this x plus 1 and broke it apart here, if these both have x, we can like factor that out and write x parentheses log 3 minus log 5. We're just getting that exponent out of it. And then that's still going to equal the opposite of log 3 over here. And so we've gotten to a point where we don't have two x's on the left anymore. We only have one x on the left. So how do we get rid of the stuff that's with x? How do we get x by itself? There's one last thing we need to do. This is multiplication. How do we undo that? Divide it. Yeah, we're going to divide by this difference. So this is going to be x is equal to the opposite of log 3 divided by the difference of log 3 and log 5. And we did that almost entirely using algebra 1 with a little bit of algebra 2 stuff at the beginning. But the process, the moves that we did basically from here on down, this is all algebra 1 from this step all the way down to here. It just includes logarithms. So let's do the division. Get a fraction going. We're going to have negative or the opposite of log 3 over log 3 minus log 5. So we're going to get a value of x that should work with both sides of that initial equation. And when we type it in, we get an answer of 2.15066, whatever else, right? So x is approximately 2.15. Take a look over at the graph real quick. What do you notice? Look at the graph on this problem. We've kind of ignored it up until now. What do you notice about the graph? Where's the point of intersection of those two functions? Or what's the x value anyway? It's 2.15. And the y value is 31.8. What we're saying here is that if we were to graph each of these as separate functions, which we could, y equals 3 to the x plus 1, y equals 5 to the x, what we're doing here is we're finding the intersection of two exponential functions, because each of these could be considered its own exponential functions. And so this is like solving a system of exponential equations. So if you're to graph both of those on the same graph and find the point of intersection, you get an x value of about 2.15. If you plug x back in here and get y, that gives you 31.8-ish. If you plug x back in here, that also gives you 31.8-ish. That's the point of intersection. So we're finding the point of intersection between two logarithmic functions if each side of the equation could be written as a logarithmic function by itself. All right, let's do the next one here. First thing we're going to do is rewrite each of these in logarithmic form. What's that going to look like? What will our new equation look like when we include logarithmic form here? Okay, what's next? Next is a word problem. So I'm going to give you 3 minutes. And I want you to try to solve this one on your own. And then once we're done with this, we'll be done for the day, and then we'll finish up the notes tomorrow. And there are 5, 6 total examples. So yeah, we'll definitely get this done tomorrow, but this will be the last one we do today. Try this one on your own. Same steps that we just went through. There's one small thing that you have to do to make this one work that I actually kind of forgot about at the beginning, so I had to adjust mine a little bit, but hopefully everybody at least has that down here at the bottom. Hopefully you all have that. Log 2 to the 3x equals log 7 to the x plus 1. Everybody have that? Okay. After that, this is where I forgot to do something. So I had to make an adjustment. I initially brought down the 3x in front of the log, and I wrote 3x log 2, and then I thought, wait a minute, that doesn't make sense. Because 2 cubed is a number. What does 2 to the third power equal? 2 times 2 times 2 is what? What's 2 cubed? Anybody? 8. All right. So this should be x log 8, not 3x log 2. X log 8 equals x plus 1 in parentheses log 7. So we're basically treating the right side like we'd use the left side on the last problem. But that 2 to the third power is a number. 2 to the third power is 8. And that's what skipped my mind on this one. I got one more step, and actually I think I almost got 2 more steps, and I was like, this is not going to work. And then I realized, oh yeah, 2 cubed is just a number. It's 8. And so then we're going to separate it out on the right side. So we're going to get x log 8 on the left, and then x log 7 plus log 7 on the right. Write it as a sum of logs. It was on this next step that I realized things were not going to work out, so I went back and adjusted. Subtract x log 7 from both sides. I got to this point here, and I thought, I can't end up factoring anything out. Other than, I could factor out x, but that would give me 3 x and then 3 log 2, but 3 log 2 is just log 2 cubed, which is log 8. So it makes more sense to multiply out 2 to the third power early in the problem as opposed to later. If you kept going, by the way, if you did write it with the 3, it would work. You just have 3 log 2 instead of log 8. But 3 log 2 is log 8. So you could have done it that way too. It doesn't make a difference. In fact, the book, it says 3 log 2, but I prefer just using log 8 because I want to get rid of that earlier than later. So it does work either way. Factor out the x. So so basically I'm just saying there's more than one way to do this problem, and I thought I messed up. I didn't mess up, but I like not having that number in front of it anyway. I'd rather multiply out those numbers. So no, it shouldn't take any more time. The answer should be 14.57. Either way, you get about 14.57. So if you had log 7 divided by 3 log 2 minus log 7, that's the same thing. And it ends up being the same answer of 14.57. I just like the look of, I feel like it has a cleaner look, not having the 3 in front of the log. It's a preference. It doesn't make a difference in terms of the answer. So we'll pause there for the day.